Okay, welcome to Intro to Programming. This will be our first webinar. The first thing I have to do is read this webinar disclaimer. The WebEx service includes, service includes a feature that allows audio and any documents and other materials exchanged reviewed during the session to be recorded. By joining the session, you automatically consent to such recordings. If you do not consent to the recording, please do not join or participate in the session. This WebEx service is intended to supplement the classroom experience. Duplication or redistribution of lecture capture recordings is prohibited without appropriate consent. Okay, that's kind of like something I have to just do right up front. Now I guess we can begin. There we go. Okay, Chapter 1. We'll start right off at the very beginning. What is a computer? This particular Introduction to Programming course presumes that nobody has previous experience in computing or programming, which is probably a bad presumption because many students do have some exposure to computers, obviously, and even computer programming. So we are going to go ahead and start right at the very beginning and identify what a computer is. A computer is a programmable electronic device that can input, process, and output data. And by outputting data, you can also store it as well. If anybody's on, please mute your phone so there isn't any background noise. So that's a computer, basically something that gets input, processes the input, and then produces output. The output can be in the form of a report. It can be to a screen, or it can be outputted to storage for later usage. Here's a diagram that kind of describes how the computer does work. If you have input, what are some input devices? Could be a keyboard, could be a microphone, could be a mouse. These are all input devices, and you would input data into the computer's random access memory, also known as RAM. Everything gets entered into RAM before it can be processed. If you want to enter or load a program comes from your storage and gets loaded into RAM. Let's say it's Microsoft Word. You would load Microsoft Word into RAM. You could go ahead and enter data. Everything goes into RAM. And when you need to process things need to be processed via random access memory. Once it's done processing, the data turns into information, and it gets sent to some output device, such as a printer or a monitor. The key concept behind this slide is that everything goes through RAM. So it's kind of important that you have enough RAM in today's world with very large amounts of data and very large programs that do need to get loaded into RAM. It's a good idea to have an awful lot of RAM space when you are purchasing a computer. By the same token, with videos and audio, a large amount of storage capacity is also a good consideration. A large C disk, they're getting up close to 1 terabyte now, so that might be something that would be worthwhile in getting. Oh, don't tell me this froze on me here. Okay, my screen just froze. All right, you know what I'm going to have to do, guys? I'm going to have to reboot. So you guys can stay put. I have to reboot because my computer froze, and I'll re-log in, and I should be rejoining probably within a minute or two. So bear with me until I come back in. Okay, I'm back, guys. Everybody still there? Julio, Mark?
Yes, I'm still here.
Okay, good. Thanks for hanging in there. And you know what? I'll tell you what I think the problem is that causes that, and that is my cursor. You know, I have this app that illuminates my cursor, and you may have seen that in the presentation. And I believe that cursor app causes this computer to freeze. All right. I don't know what happened to my. All right, I'll go get it again. Okay, so let's try it again. Let's. Oh, I got to see if I'm recording in case anybody is. Okay, it looks as though it's recording still. So. Okay, here we go. We're going to do this one more time. We'll go to previous. I'm going to stick with this cursor. I had been given some suggestions that my cursor could not be seen during these WebExes. So I went out and I got that app that illuminated it in purple. And ever since I got that, it has, I believe, caused my WebExes to freeze on me. So I'm not going to use that. We'll see if we can get through this without the illuminated cursor. And that means I'll just have to go slow with my cursor so that you guys can see where I'm pointing. All right, I think we were done with this slide here. We talked about input, process, output, and everything has to go through RAM. In class, I used a little diagram here to illustrate that when you boot up Windows, for instance, Windows is stored over here on your hard disk. It needs to get loaded into RAM. And then as you bring in Microsoft Word and browsers and other applications, everything needs to be brought into RAM. If there's any kind of calculations that need to be done in these applications, such as Word, Excel, or PowerPoint, the calculations are done over in the CPU, which is the central processing unit. The central processing unit has three major components. It has a control unit, it has an arithmetic logic unit, and it has a system clock. If you have to do a calculation like 7 times 3 over here in an application running in RAM, it will then get sent over to the CPU. The control unit is like the cop, and the cop will conduct traffic. And the control unit will determine who's been waiting the longest to do a calculation. And then once my 7 times 3 has waited its turn, it will then pass that on to the arithmetic logic unit, the ALU, and it flips the bits and calculates 7 times 3, comes up with 21, and then passes it back into the application that requested it. The control unit uses the system clock to determine who's been waiting the longest. So that's essentially, in a nutshell, how things are processed. But the key ingredient here is this RAM thing. You need to make sure you have plenty of RAM in order for you to do your processing. The CPU, you might want to have a powerful, fast chip if you have a need for very fast lightning calculations. And obviously a lot of data, you would need to have a very large hard disk. A computer consists of CPU, memory, hard disk, floppy disk, monitor, printer, and communication devices. These are all the pieces to a computer. The CPU we just talked about, that's the central processing unit. That's the brain of the computer. It retrieves instructions from memory and executes them. The CPU speed is measured in megahertz, with the megahertz equaling 1 million pulses per second. The CPU has now been improved continuously, and if you buy a PC now, you can get an Intel Pentium 4 processor at 3 gigahertz, and a gigahertz is a billion pulses per second. So your CPU is how fast this computer thinks. Memory, that's RAM, that's random access memory. A key component of RAM, or a concept of RAM, is that it is considered to be volatile. Volatile memory means that it goes away when the power source goes away. If you unplug your computer, everything in memory, everything in RAM memory is lost. If you want to be sure that you don't lose your data, then you need to go ahead and save it onto a hard disk over here in the storage devices. The disk, thumb drive, some permanent storage. That would be non-volatile memory. And then you have your communication devices, your input devices, and your output devices, which I think we kind of know about. Okay, now how is data stored? Data of various kinds, such as numbers, characters, and strings, are encoded as a series of bits, zeros and ones. Computers use zeros and ones because digital devices have two stable states, which are referred to as 0 and 1 by convention. We programmers use zeros and ones, but it's really electronic states. You can also think of it as being on or off, clockwise or counterclockwise. But the concept is it's binary. You can have only two states. It's a lot easier to think of it as zeros and ones. Programmers need not be concerned about the encoding and decoding of data, which is performed automatically by the system based upon the encoding scheme. The encoding schemes vary. For instance, the character J is represented by this bit configuration in 1 byte. A byte has 8 bits, and there are 8 bits in this configuration, and that represents the uppercase J. A small number, such as the value 3, can be stored in a single byte. If a computer needs to store a large number that cannot fit into a single byte, it uses a number of adjacent bytes. No two data can share or split a same byte. A byte is the minimum storage unit. And they give a little example over here where we have a memory address, and it looks as though it's ascending as we go down the slide. And the contents of the memory is what's represented right here. And each one of these boxes represents a byte. So the first box here in memory address 2000 is the uppercase J. Now this is using the ASCII character representation. And just quickly going through this, ASCII is a convention used by computer people around the world. And the convention is essentially to use, if we use these bits going from right to left as powers of 2, this first bit would be 2 to the 0 power, or 1. Then this is 2 to the first power, or 2s. 2 squared is 4, then 8, then 16, then 32, then 64, then 128. This 64-bit right here, this bit right here is like a zone bit that says this is going to be an ASCII character, and it's going to be uppercase. These other bits to the right of this zone bit indicate the displacement into the alphabet in powers of 2. So as I said, this is the 1s column, the 2s columns, the 4s, and the 8s. So we have a 1 in the 8 column, and then we have a 1 in the 2 column. So an 8 and a 2 would be 10. And the J is the 10th character in the alphabet. And because this bit says it's ASCII and this bit is off, it says it's uppercase. If we look at the next byte, we have the 64-bit on, and we have the 32-bit on. That says it's ASCII. That says it's going to be lowercase. And then this is the displacement into the alphabet. And we have just a 1 in the 1s column. So that would be the first character in the alphabet, which is the lowercase a. The V would be the 64-bit is on, saying it's an ASCII character representation. The next bit, the 32-bit, says that it is lowercase. And then we have 16, no 8s, a 4, and a 2. 16 and 4 and 2 is 22, so V is the 22nd character in the alphabet, and it's lowercase. Here is another A, and then the number 3. This is a value, so these are character representations. This is not a character. This is a value, and the value is simply the sum of all of the bits and whatever their associated values are. For instance, this is the ones bit, the twos bit, the 4, the 8, 16. There's no bits flipped after the twos bit. So we have a 2 and a 1. So the total value in this byte of storage is 3.
I'm sorry.
And that essentially is how. Nope. Go ahead. What do you got?
I lost my video. I've been trying to put it back. All I'm seeing is Kerry Kramer's personal room.
Okay, that is Mark speaking?
Yes, yes.
Okay, and now Julio, are you able to see the video?
The same thing happened to me.
The same thing happened to you?
Yes.
Oh my goodness. All right, so let's just see what the problem is. Okay, I bet you can see it now, right?
Yes. Well, yeah. Now again.
Oh, okay. All right. Yeah. Evidently, when I was frozen, it didn't continue my sharing of the screen. Okay, so just to kind of go through that quickly, now that you've got the slide in front of you, do I need to go through this again? Because you weren't seeing what I was showing here, but here is 1 byte of storage. This particular bit right here is the 64-bit. And the 64-bit is on, which says this is going to be an ASCII character. The next bit, which is a 32-bit, these are powers of 2 going from right to left. The 1s, the 2s, the 4s, the 8s, 16s, 32, 64, and 128. So the 64-bit is on, the 32-bit is off. The 64-bit says that this is going to be a character value. The 32-bit, which is off, says it's going to be an uppercase. And then these remaining bits identify the displacement into the alphabet. So what do we have here? We've got no 1s, we've got a 2, we've got no 4s, and we have an 8. So an 8 and a 2 adds up to 10. So J is the 10th character in the alphabet. And it's uppercase because this bit is off. The next byte, we have the 64-bit on, which says that it's going to be a character, an ASCII character. And it is going to be lowercase because this bit is on. And the remaining bits identify the displacement into the alphabet. And it's the first character in the alphabet. It's lowercase a. V, on the other hand, would be an ASCII character here, a lowercase because this bit is on. And then we have a 2, a 4, no 8s, and a 16. So a 16 and a 4 and a 2 adds up to 22. So V is the 22nd character in the alphabet. This is how your character data is being stored. Here's another A, identical to this one up here. But the 2004 memory address doesn't have character representation here. It's an actual value. And this value 3 can be simply understood to be whatever the representation is of these bytes, of these bits. The 1's bit is on, the 2's bit is on, the 4 is not on, the 8's not on, the 16, the 32, the 64, and the 128 are all off. So we just have the 2 and the 1 bit on. The 2 plus 1 is a total of 3. So this byte of storage is storing the value 3. That essentially is how the data is stored in computers using these types of representation, character data and numeric data. Storage devices, I'm sure you guys are aware of. This is CD drives and floppy disks and thumb drives, and the data that's stored on those drives is stored the same way as what we just described using the ASCII values and the numeric values. Output devices are monitors, printers. Excuse me. Monitor resolution and dot pitch. Resolution is the screen resolution, and it is measured in pixels. And the number of pixels in the horizontal and vertical dimensions of a particular display device, such as a monitor. Pixel stands for picture element. It's a combining of two terms, picture and element, and they are the tiny dots that form the image on the screen. A pixel can be comprised of three components: a red component, a green component, and a blue component, an RGB color pattern. And each one of those components can be stored in 1 byte of storage. Don't want to get into too much details on this, but you can store many, many colors in 3 bytes, with 1 byte representing every different shade of red, another byte representing every shade of blue or green, and then the third byte representing every shade of blue, the RGB color scheme. So that's resolution. It's measured in pixels. A common resolution for a 17-inch screen would be, for example, 1024 pixels by 768 pixels high. And that actually is a very low resolution screen by today's standards. They've gotten much, much sharper. The dot pitch is how close these pixels are together, and it's measured in millimeters. The smaller the dot pitch, the sharper the display. Modems have come a long way. I remember the days when we had dial-up modems, and I had a 14.4 kilobits per second modem way back in the 1980s, and it has come a long way since then. And now pretty much every household does have a high-speed, either DSL or cable modem in their premises. Okay, computer programs are known as software and instructions to the computer. You tell a computer what to do through the programs. Without programs, a computer is an empty machine. It can't do anything. Computers do not understand human languages, so you need to use computer languages to communicate with them. And then programs are written using programming languages. My very first programming language, my second language, actually my first was BASIC, but after BASIC I learned assembler, the assembly programming language. And it's a very, very low-level language. It's working with a lot of bits and bytes, and it's very tedious. The good side of learning assembler is you do understand exactly what's going on inside your computer. Nowadays, you really don't have to focus too much on very low-level languages, because the higher-level languages are much more popular, and they are very, very powerful. And because computers have gained so much power, you can use high-level languages to solve problems. 30, 40 years ago, the computers weren't that robust and that powerful, so you had to write in very low-level languages, such as assembler. Here's an example of assembly language. Here would be the instructions: add register 3 and register 2 and register 1. And this is your instruction, the add instruction. That actually gets directly translated over into machine code and gets stored in a series of zeros and ones. Higher level languages are English-like and easy to understand, and they're relatively easy to learn. For example, the following is a high-level language statement that computes the area of a circle with a radius of 5. And this you can tell area is equal to pi, which is over here on the right-hand side, r squared. Area equals 5 times 5 times 3.1415. So that the radius is 5, and when this calculation gets done, it goes from right to left. So wherever there's an equal sign, that's actually an assignment operator, which says do this calculation and then take the result of this and store it into an area in storage called area. This is an example of a high-level language, which is a lot easier to understand than the previous one that was just zeros and ones. Here are many other popular high-level languages. Java is the one that we're going to be using in this class. It was derived from originally the C programming language, and then that evolved into C++, which allowed for object-oriented programming, and now Java is a very, very powerful programming language. And the biggest, well, there are many different important features of Java, but one of the big ones is that it works with the internet. And many applications are now being developed for the internet, so Java looks to be the strategic language for today. Now, a program is written in a high-level language called a source program. That area equals 5 times 5 times 3.14, that is source code. It's written in a source program, and you need to go ahead and convert that from source code over into machine code. And then the machine code is what gets executed. The translation can be done using another programming tool called an interpreter or a compiler. So for example, in our area equals pi r squared example, you can take this and run this through an interpreter, and it will produce output. An interpreter is a little different from a compiler because an interpreter reads one statement from the source code at a time and translates it into machine code, statement by statement, and executes it right away. A compiler, on the other hand, translates the entire source code into machine code, into a file of machine code, and then that machine code file is then executed. Compiling source code into machine code oftentimes is much faster than an interpreted solution. Here's a diagram that shows you compared to the hardware. And the hardware essentially works with the operating system. We'll think of it as Windows. Application programs are loaded into RAM, and they work together with the operating system. And the user typically works with the application programs, which work with the operating system, which works with the hardware. The operating system can also work with the user for login purposes, log off, and things like that. But generally, this is the hierarchy for all of these entities. Why Java? Basically, as I said before, it's the one that's that is most compatible with the internet, and it is also portable to all different platforms. So Java runs on our cell phones, our smartphones, servers. It runs on desktops, laptops, and large mainframes. I'm not going to get into the Java history. You can read about that in the textbook. Again, I think the most important thing here is that it is architecture neutral, right? We'll run it anywhere. With the Java virtual machine, you can write a program one time and run it on any platform. Back in the olden days, back in the 80s and the 90s, if I wrote a program on a particular computer, it could only run on that computer. If I wanted to take that program and run it on some other device, I'd have to rewrite the whole program. So now Java is portable and architecture neutral. It is very, very flexible. Here's the history of the Java development kit. When you download NetBeans, for instance, along with NetBeans comes the Java development kit, or the JDK. And inside the JDK has all of your tools, your compiler. It has all of your other tools that you can use in developing your solutions. The JDK versions, starting in 1995, started with JDK 1.02, and currently right now we're working with JDK 1.8, which which came out in 2014. It's also known as Java 8 or JDK 8. In this class, we'll be using the Java Standard Edition, the J2SE, and that's where we're developing client-side standalone applications. You can also use J2EE, which is for server-side applications, Java Micro Edition, J2ME, which can be used for mobile devices, and this is our book we'll be using, the first one, the Java Standard Edition. We're going to be using NetBeans, and hopefully both of you or whoever else has joined have been using NetBeans to submit your assignments. There is also Eclipse, which is another IDE. An IDE is an integrated development environment, and the two strategic ones are NetBeans and Eclipse. In this class, we'll be using exclusively NetBeans. Here's a typical example of a program, and I'll just go through the pieces here. This first line here has two forward slashes, which indicates that this is a line comment. And in this line comment, it says this program prints "Welcome to Java." The next line here has a public modifier and then an identifier which says that this is a class, and the class name is going to be welcome. The class starts here at this left curly brace and ends down here at this right curly brace. It's very important that you indent and use this structure when trying to write your code and read your code and leave it for somebody else to go ahead and maintain, because these can be placed anywhere. The compiler doesn't really care, but other programmers reading your code certainly do. So it's important that you put your curly brace on the same line as the welcome, the name of the class, and then directly underneath the P in public, put your closing curly brace. This identifies this particular program as a class. Inside this class, we're going to have a method. These are modifiers, public static, and then void main. This is a method, the main method. We know it's a method because it has parentheses. It has an opening parentheses and a closing parentheses. Inside the parentheses are what's known as parameters. And parameters are separated by commas. In this particular case, the main method has only one parameter. There are no commas in here, so it has one parameter. The parameter is args. That's the name of the parameter, and it is going to be of a string array. That's what this means. We'll talk about this later on in the semester, but essentially this main method gets past a parameter of strings, a string array. Normally, you don't pass it anything, but later on in the end of the semester, we're going to pass an actual string to the main method. So you can go ahead and just use this as your structure: public static void main, open paren, string, left bracket, right bracket, and then args, close the parentheses, and then open up your main method with another curly brace on the same line as the main method. The main method ends on this curly brace, directly underneath the P in its public. This main method has only one statement. It is system.out.println, and it says "Welcome to Java." This will print "Welcome to Java" to the console. This is a string. It is surrounded in double quotes, so whenever you want to put out a string, it needs to be put out in double quotes. Println here is a method in this library, in the system library. We know it's a method because it has parentheses. It's got an open parentheses and a closing parenthesis. And inside are the parameters. There's only one because there's no commas, and this parameter is a string, and that essentially says pass this string to this little program, this little method called println, and it will go ahead and take it and send it to the console. You can also write code. Instead of using NetBeans, you can also use NotePad and type this code in and use the DOS prompts to do that. I'm not going to spend any time in tonight's webinar on the DOS, but you can follow the instructions in the in-class assignment and just see how that works. That's originally how code was written, and now it has evolved into the integrated development environments, IDEs, such as NetBeans, which makes life a lot easier for all of us. You can also use WordPad. Here's another diagram that identifies your simple program, which says Welcome to Java. It's of the same structure that we just went through. Here's your source code. We wrote it in NotePad, and we store it on some disk. This source code right here is stored on the disk, and then you need to compile this code. Well, there's a program in the Java Development Kit called Java-C, which will compile this welcome class called welcome.java file. If there is a clean compile, it creates what's known as bytecode. And this bytecode looks something similar to this over here. Not necessary to understand that, but just understand that it is bytecode. And then you can run the bytecode by invoking this Java program, which will then run the welcome.java, the welcome.class file. And then you're going to get the result, Welcome to Java, displayed to the console. If you have compiling errors, you have to go back in here and re-look at your source code and find out if you're missing a semicolon or parentheses or a double quote or something like that. Here's another diagram. It basically says the same thing that I've been saying, so I'm going to skip over that. And likewise, this is kind of a hierarchy here where the Java Development Kit, which if you look at when you downloaded NetBeans, it will store it on your C disk. And inside the Java Development Kit is the JRE, the Java Runtime Environment, and inside the Java Runtime Environment is the Java Virtual Machine. So you get an understanding of the hierarchy of those three components. Here's a trace. I'm not going to go through that because I just went through it. Welcome with 3 messages and compute expression. I'm going to go over to NetBeans for a moment. And I'm going to execute a program. Where is my NetBeans? Over here. I had this all queued up and ready to go before it froze. I'm going to do File, Open Project. And by the way, all of my assignments, there are examples of what I'm expecting you to do in the sample programs posted in Blackboard. One of the programs for Chapter 1 is, I think, called Simple Arithmetic. Right here. Okay, here is a different structured solution than what we've been talking about before. We were writing code in welcome.java and compiling it and creating another file called welcome.class. And then we would run using the Java instruction in the DOS prompt to run the class file welcome.class. Over here in NetBeans, there's a different structure to it. You have a whole bunch of folders within folders and a project, and within a project and packages. Over here, you'll see here's where the source packages are. I called this class Simple Arithmetic, and it's very important that you understand that Java is case sensitive. When you're calling a class, or when you are creating a class, you need to go ahead and put the first letter in uppercase of every word in that particular class. So we have 2 words, Simple Arithmetic. They are butted next to one another, and it's uppercase S and uppercase A. This is called Simple Arithmetic. The first statement up here is the package statement. This corresponds with this particular package, Simple Arithmetic, all in lowercase. The next is we're going to import this java.swing.jOptionPane class, and that allows us to invoke this method down here, this show message dialog method inside this class. and it's got some parameters. The first parameter is null, and then the second parameter is this calculation with a string included. So here's your import statement, and then the structure is similar to what we discussed. You've got public class simple arithmetic, you've got your opening curly brace, and the beauty behind NetBeans is that it will show you the corresponding closing brace. All I need to do is click to the right of this curly brace, and it shows me that I have a closing curly brace directly underneath this public. Underneath the class is the public static void main method with the string array called args. And I've got an opening curly brace, and here's my associated closing curly brace. This next is a line comment, display the results, and I have in here system.out.println a string incorrect addition, and it goes from there to there. Inside the, I'll get this one here, from there to there. This is going to be treated as a string, whatever you put inside there. Next is a plus sign. The plus sign in Java can mean one of two things. It can mean either addition or it can mean concatenation. Addition obviously is to take two values like 3 and 4 and put them together and come up with 7. Or it could mean concatenation. Concatenation means taking one thing and butting it up directly next to the other thing. So for instance, in here we have a string. Inside the string it says incorrect addition, colon 3 plus 4 equals, and then that's the end of the string. In this particular case, we have a string and a value. And this plus sign needs to be interpreted by the compiler, and it's going to say, I got a string and I got a value. You don't add a string and a value together, you add a value and a value together. So it will therefore consider this as a concatenation sign rather than a plus sign. And that's why when I execute this particular program, you will see, it's going to come out down here, it has incorrect addition. This J option pane show message dialog box is what just popped up here. I'll move it over here to get it out of the way. But you'll see incorrect addition, 3 plus 4 equals, this is my string, and it used concatenation, and it outputted 34, which is incorrect. The correct addition would be to go ahead and system.out.println and do this character string all the way to here. And then I have my plus sign, and then I put in parentheses 3 plus 4. Now there's an order of precedence in Java. If you put things in parentheses, it will do those first. It will do that operation first. So I put the 3 plus 4 in parentheses. Now the compiler will say I've got a value 3 and I've got a value 4. What do I want to do? Well, values you add. So it will add the 3 and the 4 and come up with 7. And then the next operation is a string and a plus sign and a 7. Well, the compiler says we've got a string and a value. I'm going to concatenate that. So this string will then get concatenated with this particular result, and you're going to get the correct addition is going to be equal to 7, demonstrated down here. Okay, here's some other simple arithmetic. I just do this the string so we can see it, but now I put in parentheses 7 minus 2, and I will get 5 down here. It gets concatenated. Multiplication, good idea when you have multiplication and addition to use parentheses. Whenever there is addition and subtraction, multiplication and division, it will always do multiplication and division first. After it's done with its multiplication and division, it will then do the addition and subtraction. If you have multiple multiplications and divisions, it will go left to right. If it's the same order of precedence, the program will execute left to right. So we have 8 times 5 is going to be 45 right here. That will get, I'm sorry, 8 times 5 is 40. A very important thing down here is integer division. We have integer division, and I'm doing 19 divided by 6. In Java, if you have two integers and they're being divided, you're only going to get integer division, which means 19 divided by 6 is going to be equal to 3. Integer division keeps the quotient and throws the remainder away. And that doesn't seem to be too accurate, because down here we have integer division. 19 divided by 6 is equal to 3. That is incorrect. The precise calculation would need to be identified by putting a decimal point in either the numerator or the denominator, or both. So I've rewritten this statement so that it calculates 19 divided by 6.0. Then Java will say, this needs more precise results, so the 0.0 will then yield the correct answer of 3.1 and 6 repeating. Very important concept here, knowing that this is integer division right here, and this is more precise division. Don't make those mistakes. When you have multiple operations, as I said before, addition and division, use parentheses. The calculations will be done by the order of precedence. Parentheses first, the PEMDAS, if you remember PEMDAS. Parentheses, exponentiation, multiplication, division, addition, and subtraction, in that order. Now, the next statement here is an approximation of pi. This particular character right here, it's embedded within a string, and this is an escape character. This \u is an escape character, and this is a Unicode representation of the Greek letter pi. All the characters on a keyboard around the world in Java are stored in 2 bytes of storage. That includes many wingdings and Greek letters and kanji characters and Arabic letters that we need 2 bytes of storage in order to store all of those associated characters. So this particular expression says this is an escape Unicode character, and it is represented in 4 hexadecimal characters, 03C0. And we'll get more into hexadecimal later on this semester, but that will go ahead and escape out of this string and replace it with the pi symbol, the Greek pi symbol. And what I did was I used 22/7, and I went ahead and used 22.0 divided by 7 in order to get 3.1428. So that is introducing other characters that are not on your keyboard into console output or to a printer or to a terminal. The last statement I just want to introduce to you, the power of object-oriented programming. In this particular example, I don't know what happened to my dialog box here. It's somewhere underneath things, but let's just stop that, and I'll run it again so we can generate this. But this dialog box right here is generated by this statement right here, this JOption pane show message dialog. And this is doing nothing more than putting a string out, multiple operations, 2 plus 10 divided by 5 is equal to 2.4. And I had to make sure that I put in the 5.0 so that I got precise division. Otherwise, it would get integer division, and it would be grossly inaccurate. And this plus sign, you can go ahead and span multiple lines. This is a concatenation sign, and we're going to go ahead and do this calculation here, and it gets stored inside this dialog box. All the code for this dialog box is over here in this method, in the JOption pane class, over here in the javax.swing library. We'll get more into that later on in the semester, and that's actually going to be an introduction to the next course after the Intro to Programming, the Object-Oriented Programming class using Java. Hopefully you'll take that next semester. So that is simple arithmetic. Let's get back over to the PowerPoint and let's continue on. I'm going to skip over this working in the DOS prompts. The anatomy of a Java program. Okay, obviously this is all the different pieces and the parts of a Java program. We'll talk about the class name, the main method, the statements, the terminator, statement terminators, and reserved words, comments, and blocks. We talked about them a lot already, so I'm not going to spend a lot of time on them. But obviously the class name is the name that comes right after the word class. This is a reserved word, as is public, and this is the class name. Class names start with an uppercase letter. We use simple arithmetic. We used hello world, and they all have uppercase first letters for each word in the class name. The next is the main method. We discussed that. We know it's a method because it has parentheses. Inside the parentheses are parameters. When a parameter gets filled with a particular value, that becomes an argument to that method. And inside this main method is a statement. And the statement, we know it's a statement because it ends in a semicolon. All statements in Java end in semicolons. Right here. Reserved words are public and class, public, static, void. These are all words you cannot use when you decide to create your own class name, such as welcome or simple arithmetic or lab 1 or in class 1 or pre-lab 1 or any of those other classes that we've used so far. You cannot use these reserved words. These are specific and special to the compiler so that it knows exactly how to compile your code. We've discussed this already. Here's your opening curly brace and your closing curly brace for the class block. Right here is the opening curly brace and your corresponding closing curly brace for your method block. Here are the curly braces. They open and close the blocks. Your parentheses, these are used with methods. Your brackets denote an array. So the string with the brackets is a string array that's called args in your main method. We'll talk more about arrays later on in the semester. The 2 forward slashes or double slashes are to denote a line comment. Opening and closing quotation marks are these double quotes, and they are used for strings and the semicolon. I'm going to pause right now just to focus in on these double quotes here. Many keyboard characters for double quotes have sometimes like a different double quote than what we're looking at here. Sometimes you might see a curled double quote, an opening close quote that curls to the right, and another corresponding double quote that curls to the left. If you see that, that's going to be a problem in your NetBeans compiling, because when the NetBeans compiler tries to compile your code, it's not going to recognize those different double quotes. And they're going to look rather similar, almost identical to you. And you're going to wonder, well, why can't I compile my program? And it's because the double quotes that are in your program are not the ones it's expecting. If you're having trouble with that, I would just go ahead and delete the left curly quote and replace it with a single straight up and down double quote. And likewise, the same thing if you have one for a closing quote. Make sure that the quotes that are in your Java program are straight up and down. Otherwise, you will not be able to compile. How does that happen? Usually when you copy code from a PowerPoint or from a Word document or some other document, it will use a different quote in the ASCII character representation that the NetBeans compiler is not going to like. Hopefully I've saved you a lot of headaches and aggravation by focusing in on that. Okay, so here's the example of the closing the curly braces. We don't need to go through that. Here's for parentheses. Here's for semicolon, the forward slashes, and again the double quotes. All right, now I'm going to start focusing in on programming style and documentation. This is as critical, almost as critical as getting your code correct. We're going to look at appropriate comments, naming conventions, proper indentation, spacing of lines, and also block styles. Make sure you use appropriate comments. You can use line comments or you can use block comments. Line comments we know are 2 forward slashes, and block comments start with a forward slash and an asterisk, and will continue on until the compiler sees the corresponding asterisk and a slash. Anything therein is going to be considered a comment. That would be a block comment. When you write a program, you should go ahead and include your name, your class, section, instructor, date, and brief description at the beginning of the program. Now, that's what the book tells you to do, and that's what Liang is asking you to do, but I've actually modified that so that you adhere more to industry standards. So I kind of created a program documentation header block for you to use, which has the program name, the program description, the author, the date, and a change control section for the next person that comes in that might have to make a change to your program. So I'd like you to use that in your assignments so that it looks more like it's business-oriented or industry-related. Naming conventions. Choose meaningful and descriptive names. Class names, remember, capitalize the first letter of each word. For example, compute expression, the uppercase C and the uppercase E. Indentation. Indent 2 spaces. And spacing, use a blank line to separate segments of code. Here's one particular example. There's different block styles. The block style that we're going to be using in this class and also in your textbook is the end of line style. This first style, this next line style, where you basically write public class test and skip to the next line and put your curly brace. Well, yeah, that does correspond nicely to the closing curly brace, and it also corresponds nicely for the main method, but it spaces your program out unnecessarily so, and it can also cause confusion when you start dealing with nested blocks. So the industry has kind of migrated over to the end of line style, which looks like this, where you have it right at the end of this line, and you open up your curly brace, and you have your corresponding closing curly brace directly underneath the P in public, the modifier for the class. So we're going to stick to that in this class. Please write all your code using this convention. Okay, programming errors. There are syntax errors, runtime errors, and logic errors. Syntax errors are detected by the compiler. I'm sure you've seen plenty of them. As you write your code, you'll see red squigglies, you'll see red balloons, and up in the right-hand corner of your NetBeans, you'll see a red block which says that you have some compile errors. You need to fix those. You cannot submit anything to me that has compile errors on it, or I will take significant points off. You need to fix those. Syntax errors could be a missing semicolon, one too many parentheses, you don't have corresponding left and right parentheses, you have one too many right parentheses, not enough, whatever, or it could be anything else that the compiler is looking for that you've omitted. Runtime errors are cause the program to abort or abend. Abend is another shortening of 2 terms, abnormal ending, and abend is the term that is used in the programming community. That means that you had no syntax errors, but something caused your program to end abnormally. And then the last category is logic errors, and those produce an incorrect result. No syntax errors, it runs fine, but you get the wrong results. That would be a logic error. Here is an example of a syntax error. If we look through this, starting right up at the top, public class shows syntax errors. That looks fine. We've got a closing curly brace, public static. We are missing void. There is no void word in here. So that is going to be a problem. We need to put public static void main. And string is okay with the opening and closing braces, brackets. And then we have system.out.println. We are missing a double quote here. So those would generate syntax errors, and you would need to fix those before you could run your program. Here's an example or an exercise for you to go ahead and do at your convenience. I created a whole bunch of errors inside this program, and you can go ahead and try and identify all the different errors, the syntax errors that I created. One thing, and this should look familiar to you, is your calculation of pi. Make sure you also put 1.0, 1.0, 1.0, 1.0 in order to get precise division. Otherwise, these fractions all will yield integer division, and you will have a grossly inaccurate calculation and result. Here is the solution to that particular exercise. I put all of my corrections in red, so you can check your work. A runtime error would be the result of this particular statement. We've got everything fine here. Public class show runtime errors, public static void main, and we have system.out.println 1 divided by 0. We cannot divide by 0. Can't be done on this planet. Maybe on some other universe they permit it, but right here on the good old Earth, we do not divide by 0. That's going to cause problems, and this will get a runtime error. When you run this and try and divide by 0, you will get an error. You need to fix this somehow. A logic error. Here's where, for instance, if you're converting Celsius to Fahrenheit or vice versa, you could go ahead and accidentally put the parentheses in the wrong spot. I don't think that this is incorrect. I actually think this is correct, but where we get a logic error is we didn't put precise division. We didn't put 9.0 and or 5.0. So this is going to be 9 divided by 5 is going to be 1 in integer division. And we're going to get 1 times 35 plus 32. 1 times 35 is 35 plus 32 is 67. That is an incorrect conversion of Celsius to Fahrenheit. If you put 9.0 divided by 5, well, now you're going to get more precise. It's going to be 1.8 times 35. And I think the result gets up into the 90s. So that would be an example of a logic error. That takes us to the end of Chapter 1. Are there any questions?
I don't have any questions.
Everybody okay?
Yes.
All right. How about the assignments? I gave you 2 in-class assignments, and I gave you 2 labs. In class 1 and in class, I'm sorry, if you're, no, you guys are in the online section, so obviously you don't have in class, I call them pre-labs. So you have a pre-lab 1 and a pre-lab 1A, and a lab 1 and a lab 1A. For those that are on, do you have any questions that I could answer, or difficulties or misunderstandings about those assignments?
At this point, should we just stick to Chapter 1 in order to finish those assignments, so no declaration of variables or things like that?
No declaration of variables. That's a good point. Some people have had programming before, and I'm going to insist that if you have an assignment in Chapter 1, I don't want you to use Chapter 3's skills to solve Chapter 1's problems. You understand?
Okay.
Okay, because, I mean, that's just not fair. I want you to do it using the skills of the current chapter or the previous chapters, but no future chapters.
Okay, perfect.
Okay?
Okay.
Any other questions?
No.
No? Okay,
Well,
everybody go ahead. Who's next?
This is Julio. The other question that I had is, I think it was either one of the pre-labs or lab 1, where the assignment is specifically to use only one print line statement. And so my question is, in future assignments, does it really matter if you need to print out, a series of statements to make it in one, or to do a series of print line statements?
Julio, I'm not aware of me giving an assignment that said you can only use one print line statement.
Well, I think it's the very first pre-lab in which you do your initials, right?
Oh yeah, no, no. Actually, I would want you to use multiple print line statements. That
Okay,
would be
well,
like very difficult to do.
well,
Yeah.
because at some point it says, use /n to move to the next line in your print line statement. So I assume that you wanted us for that particular assignment to use only one print line, which I did, and I think the output comes out correctly. But it was just a question.
Yeah, no, that's a real good question. And for the first couple of assignments, you can use either approach. I didn't want to confuse people with the /n, but if you've been exposed to that, and I think I did briefly describe it, the /n is another escape character that goes to a new line. That gets embedded inside the quotes, the double quotes, so you can go ahead and use a new line symbol inside your quotes, and it will go to the next line. So that's certainly permissible. You can use that.
Okay.
Okay. Any other questions? Anything else, Julio? We also have Mark still on, hopefully?
Yep, I'm good.
All is good? All right, no questions on how the class is going to be run, okay? This is our first webinar, and I hope that you guys understand the routine now. These will be due every week methodically, and I will grade your Lab 1s after the last deadline, which is Lab 1's last deadline was last night, right? It was Wednesday night. So I will get around to the grading. I've got some 70-something labs to grade, so it's going to take me some time to do. But I normally will try and get them done on Thursday or Friday after the Wednesday last deadline. Okay, so I'll try and get to your Lab 1 and grade it. It will be over in your My Grades tab in Blackboard once I've graded it. And I'll usually put a very brief description on things that you may have gotten wrong or suggestions or whatever inside the My Grades tool.
Great.
Okay. If there are no further questions, I guess we can wrap it up for tonight. My intention is to do these for every end of chapter. Chapter 1 was a 2-week chapter because I got a lot of people coming and going, and a lot of people that don't know programming right out of the blocks. But Chapter 2, we're going to go quickly through. That'll only be 1 week. And if I see it necessary, I'll probably do another webinar similar to this one, and we can go ahead and discuss any confusion or uncertainty in that webinar, and that might be, in all likelihood, next Thursday. So I'll send another email out or Blackboard message notifying everybody. Okay, so no other questions? Okay, very good, guys. Okay, thanks for participating. And any questions, shoot me a Blackboard message or just throw it in the discussion tool.
All right, thank you very much.
Have a good one.
Okay, yep, have a good night, guys.
Bye.
All right, good night.
Have a good night.
Bye.